Welcome to the second part of the problem-solving session for Chapter 23. And we begin where we left off in the Part 1 session. Question 7 says the following. We have a charge Q with a mass of 2 e to the minus 3 kilograms. Notice the book gave us 2 grams, which is 2 e to the minus 3 kilograms. And it is suspended from a light string of length L equals to 0.2 meters. This is L right here, 0.2 meters. The book gives us 20 centimeters. Now, this charge of mass M is located in the presence of a uniform electric field directed along the I-hat direction. That is, every point in the space around this charge, the value of the electric field is constant. Again, there's a source charge that produced this electric field, but we really don't care anything about the source charge other than the fact that the electric field has this value in the region that surrounds our charge in question. Anyhow, this charge is in equilibrium. It is on the surface of the Earth. And the reason we know it's in equilibrium is that the angle which the string makes with the vertical is fixed at 15 degrees. So the question is this: what must be the value of Q in order for this to be true? Now, if you recall the previous problem, the one that we ended in Part 1, we were asking what was the mass of the charge if it floated on the surface of the Earth. This time we're asking what is the charge of this mass if it floats, essentially, not necessarily floats because there's a string, but if it hangs motionless at this 15-degree angle. So very similar in that this is an equilibrium problem, except that we are going to have to work in 2 dimensions. First, however, let's draw some pertinent information. I'll go ahead and just make use of the drawing that they provide us to begin to label and examine the forces that act on this charge. Well, of course, there's gravity. We can't get away from it. Fg equals mg because it is on the surface of the Earth. Because it's attached to a string, there is also tension along the string. And this tension is going to have, of course, components. It's going to have a vertical component, and if there are no other forces along the y direction, that vertical component we expect should balance out the force of gravity. There will also be a horizontal component, Tx. Now, what does this component balance? Well, let's see. If there was no other force acting along the horizontal, our charge would be accelerating in the x direction. But we're told to determine the value of Q such that there is no acceleration, both in the x direction and in the y direction. One other thing here, we want to just make a note. This is a right triangle, even though it doesn't look like it. This is a 15-degree angle because the string makes a 15-degree angle with the vertical here and a 15-degree angle with the vertical here. So now we can go ahead and write the component expressions for the tension T. Because Ty is adjacent to the component Ty, to the angle that is, we get Ty is T cosine of 15, Tx is T sine of 15 degrees. And notice that it's directed along the negative x direction. So we better have a negative sign there to indicate that this is so. Now, we have gravity, we have tension, and we have the electric field. What effect does the electric field have on this charge? Well, because again of the equilibrium condition, remember, everything along x must equal 0, everything along y must equal 0, and therefore if Tx didn't have anything to balance it out, then this would no longer be true. So what we can say is that there is an Fe opposite to the direction of Tx, and we know that the electric force on a charge in the presence of an electric field is equal to QE. Further, we note that the electric force is in the direction of the electric field, therefore our Q must be a positive charge. Remember, when Q is a positive charge, the force on Q will be in the direction of E. If Q was a negative charge, the force on Q, the electric force that is, will be opposite the direction of the electric field. The electric field's in the positive I-hat direction, Fe is in the positive I-hat direction, Q must be a positive number. Well, there are no other forces acting on our charge, so let's see what we get out of it. Well, first condition, that the sum of the forces in the X must equal 0 minus T sine of 15 degrees equals Q times E. Well, let's see. We know E. We don't know Q. In fact, that's what they asked us to solve for. We know sine of 15, but we don't know T. Therefore, this is a positive and these add up to 0, which means that if we solve for Q, that is take QE to the right-hand side of the equation, then the negative sign that will be placed in front of QE balances the negative sign in front of T, and so Q is equal to T sine of 15 divided by E. Now remember, we know E and we know sine of 15, but we don't know T. Well, there is the old saying, the number of unknowns must match the number of equations. So, to the rescue, sum of Fy equals 0. Well, we come over here, T cosine of 15 positive minus mg equals 0. Take mg to the right-hand side. That gives us T equals mg. Now I'm going to divide by cosine of 15. So I can actually get a value for T. And as soon as I do have a value for T, I'm going to plug it into the Q expression so I can actually solve for Q. Well, I'm going to plug in all my numbers. 2e to the minus 3 kilograms times 9.8 divided by the cosine of 15 degrees, and I get 0.0203 newtons, provided I have not made a calculator error. This I now plug into here, and so I get Q equals 5.25 e to the minus 6 coulombs, again provided that I haven't made a calculator error, which you will, I'm sure, be checking for me and letting me know if I did. Next problem. Oops. I need to go lower. There we go. Question 8 gives us 3-point particles, particularly charges, Q1, 5 nanocoulombs, Q2, 6 nanocoulombs, Q3, negative 3 nanocoulombs. They are arranged on the XY plane as shown. And the first part here, never mind that this has been converted to a dot, it's part A. Find the electric field at the origin. B. Use the result of part A to find the electric force on charge 1. Now, back to part A. Note that the charge which is placed at the origin, namely Q1, is not going to contribute to the electric field at this point. Now, that's very important because this is the source charge for the electric field at the origin. This is a source charge for the electric field at the origin, but a charge at its own location cannot be a source of the electric field. In other words, Q plus Q, this little q, can be a source at any space other than the point which it happens to exist in. So what we have to take into account here is that we have two source charges, and each of these will contribute some quantity to the electric field at the origin. Well, the first part, or the best way to begin this problem is to say to ourselves, all right, ignore this plus Q at the origin. Pretend we could just remove it from there right away. Well, let's see if we can do a redraw where this positive Q is not there to interfere with the work that we're going to do. And we'll put plus Q here, and we'll put minus Q here. Okay, and plus Q here is Q2, which did not come out for some reason, positive 6 e to the minus 9 coulomb, and minus Q here is Q3, in fact, so that's equal to, and actually we don't want the plus here, the minus or the plus here, because we just want to write the value. It's minus 3 e to the minus 9 coulomb. All right, well, the best approach is to begin individually with these source charges. Let's say we want to focus only on Q3 as a source charge. What is it going to produce for us at the origin? Well, the first thing we want to do is to get the direction. And the way that we get the direction of the electric field due to a source charge is that we imagine that we could put a little proton at the origin. And we ask ourselves, in what direction does that proton feel a force due to Q3? Well, protons are positive charges, Q3 is a negative charge, therefore it will feel a force towards Q3. That is the direction of the electric field at the origin due to Q3 as a source charge. Next, consider the proton back at the origin and ask yourself, in what direction does the proton feel a force due to the source charge Q2? Well, because Q2 is positive, you know this proton is going to feel repulsed by, oops, let me go ahead and put my little vector there for E3, by Q2, and therefore will feel a force away from Q2. That then determines the direction of the electric field at the origin due to Q2 as a source charge. Any other charges there that could be source charges? No, because remember that little plus Q is not a source charge, cannot create an electric field at its own location in space. All right, well, once we have done this, now we're beginning to move further. We have directions, we know components. Hey, E2 is only going to have a negative E2x. In other words, it lies entirely along the negative x-axis, does not have a projection on y. It is negative because it points to the left. E3 points downward, so it too is negative, but it only has a component in the y direction. Well, just like we did with Coulomb's law in the problem in part 1, we are now going to first obtain the magnitudes of these vectors. E2 is given by K, Q2 magnitude, now this is very important, and again, Q2 is positive, so it doesn't matter there, but it will when it's Q3, divided by the distance of separation. We can call this R2 if we wish, or we can just simply substitute the numerical value. But anyway, it's R2, and of course it's squared. So let's go ahead and put in our numbers. 8.99 e to the 9. Q2 is 6 e to the minus 9 divided by 0.3 meters squared. That gives us a value of E2 rounded to 3 significant digits of 599 newtons per coulomb. Good. Now let's do the same for E3. Magnitude of E3, K, magnitude of Q3, divided by R3 squared. And here again, R3 would of course be the distance between the origin and Q3. All right, substituting our numbers, 8.99 e to the 9. What do I put for Q3? 3e to the minus 9 coulomb. Notice that I don't put minus 3e. Why is that? Because again, I already know the direction of the component. I know the sign of the component, therefore, and right now all I'm doing is working with magnitude. Okay, well, if my calculator gives me the corrected values, this is what I get for E3, 2500 newtons per coulomb. And now I'm ready to write my vectors. Well, let me begin with E3. The vector E3 has 0 I hat component and a negative 2500 j hat component with my unit of Newton per coulomb. E2, on the other hand, has minus 599 I hat component plus 0 j hat component with my unit Newton per coulomb. So now, if I want the net electric field at the origin due to both of these E3 and E2 source charges, I just add the component. 0 plus negative 599 gives me minus 599 I hat, minus 2500 plus 0 j hat gives me minus 2500 j hat newtons per coulomb. And that solves part A of the question. Now, part B, if you recall, asked, use the results of part A to determine the net force on the little charge Q, little q, which we ignored in part A altogether because it did not contribute to the electric field. But now we are going to insert it at the origin and say, well, we know the value of the electric field at the origin. We've just put a positive charge Q there, and we want to know what is the force on this charge. Well, remember, once you know the value of the electric field at any point in space, if you put a charge there, you can get the force on the charge as the product of Q times the electric field. Well, let's see. Q, 5e to the minus 9 coulombs, and it's positive, so we don't even really have to put a plus sign there. Minus 599 I hat minus 25. Let's see, I lost my pencil. 25 j hat newtons per coulomb. Multiply everything out, and I get negative 3 e to the minus 6 I hat, negative 1.25 e to the negative 5 j hat newtons. That is, provided I have not made a numerical error. That is the solution to part B. So notice I did not have to use Coulomb's law to get part B. And so anytime you have calculated the electric field at a point in space, and somebody puts a charge there and says, what's the force on that charge? All you have to do is to take the product of your charge, the one that's been placed at that point, and multiply it with the value of the electric field, and the problem is solved. Next question. Question 9 asks us to calculate, well, before we actually get to the calculation part, it says the following. A rod which has a length L carries a uniform positive charge distributed along its length. The total value, when we multiply all the little bits of charge along this line, we are told the total value is big Q. Calculate the electric field at the origin, which this source, that is this uniform positively charged rod, produces at this point in space. So notice this time we don't have a single particle, which is a source charge, like the previous problem where we wanted the electric field at the origin. We happen to have two source charges, but they were point particles. This time we have a distribution of source charge. And so we have to consider the effect of every little tiny quantity of charge that will collectively add to the value of the electric field at the origin. So in other words, what I've tried to draw here, although it appears big enough, is little point particles, little infinitesimal quantities of charge, beginning at the left end of the rod, at distance a from the origin, and ending at the right side of the rod, which is a distance L plus a from the origin. Well, what we want to do is, like the previous problem, we want to put a proton at the origin. And then we want to ask ourselves, well, let's just say that we took this as our representative infinitesimal quantity of charge. In what direction would my proton feel a force due to this being the source of the electric field? Well, because the rod is positively charged, so is this little infinitesimal amount. And so my proton is going to want to make a quick getaway. And so here you can see that the direction of the electric field, and I'm going to go further to write this as dE. dE at the origin is in the negative dEx direction. Now, why did I write dE? Because this little quantity of charge is dQ. Instead of writing Q as a point particle, I'm going to write it as dQ. Now, here's where we make use of the charge density. We know that because we're told uniform positive charge, we know in this case one dimension, the charge density, the linear charge density, lambda, equals total Q, total amount of charge, which they told us was capital Q, divided by the total length of the rod. Now, it is also true that lambda, because this is a constant, is equal to infinitesimal quantity of charge, little dq, over infinitesimal length, little dx. And so what I can do here is I can make a substitution for dq. If I solve for dq, dq is equal to q over L times dx. And q over L, don't forget, is lambda, right? Because that's how we defined it. And so you can see here, I can write this little dq. And by the way, our book chose to use this as the representative dq. It doesn't matter. All we want to say is that little dq is equal to lambda, and lambda equals total q over total L, total length, times dx. Now, where is this little dq located from the origin? Well, we're going to say that this is the distance x, but we're going to tell our integral, our summing machine, where to begin summing the dq's, namely at x equals a, and where to end summing the dq's, which will be at x equals L plus a. Well, we're not done yet. We next proceed to write the form of dE in terms of the magnitude, just like we've done all along. K this time dq, not q, but dq, divided by x squared. Why? Because my little dq here is at a distance x from the origin. I make a substitution now for the quantities that I know. dq equals big Q over L times dx over x squared. And of course, I could just make this one line. It doesn't matter. All right, so now I am ready to look at the components of dE. Well, dE is going to have only an x component, and it will be negative since it points in the negative x direction. It will have no y component, so I don't even need to worry about j hat. So now my task is to determine dEx, and then I'll know that dE is the negative of that value. Well, let's see. Because dE lies entirely along the x-axis in the negative x direction, then dEx is negative. It's entirely the magnitude of the vector q kq dx over L times x squared. And now I am ready to take the integral of dEx, the integral, of course, of what equals dEx, and therefore obtain the value of Ex. Well, let's see. We've got a bunch of constants here that can come out of the integral. Minus kq over L, and let's go ahead and put I hat here, dx over x squared. Where do my little dq's first appear? At x equals a. Where do they end? At x equals L plus a. So now I can go ahead and solve the integral. Dx over x squared is minus 1 over x. Put in my endpoints a, L plus a, little bit of algebraic manipulation, minus kq over Li hat times, let's see, minus 1 over L plus a, plus, because it's minus minus, 1 over a. If I want to make this look better, let's say more aesthetically speaking, then I can take a, multiply here to get minus a, L plus a multiply here over the denominator, which would be a times L plus a, make a little, well, let's go ahead and work it out so that there's no little errors that creep up. Well, we have minus a plus L plus a divided by a times L plus a. Well, this positive a added to this negative a is 0. This L cancels that L. And so aesthetically speaking, my expression becomes k times q. And they haven't given us any numbers, but presumably they would tell us what the value of total q is, what the value of a was, what the value of little l was, and our work is done. This is the component of E in the x direction. It's negative. Let's not forget the unit. And so the vector itself, E, is the component minus kq in the negative x direction. Next problem. Well, this one came out a mess, so we're going to have to just redraw it because for whatever reason these images didn't translate very well. Well, we have another one-dimensional problem, and I will go ahead and try to make a better drawing for us. We have now a ring of charge, not a straight line, but a ring. But here our ring has no width, so it's for all our purposes is the same line that we had before the rod, but it's bent into a circle. And we're asked to determine the value of the electric field at the origin along the axis of this ring, but right at the very center of it. Well, here again, we have to make note of the fact that it's uniform charge, and so lambda here is total charge, which they told us was Q, capital Q, divided by the total length of this ring. Well, the total length is the arc length, the length of the perimeter, which is the circumference of this ring. And the circumference was given by the letter A. So 2 pi A is the total circumference of this ring, but that will also be equal to dq over a component of arc length. Okay? Well, let's see. If we go ahead and choose this little arc right here, and so this is our representative dq, dq is equal to lambda ds. ds is equal to a d theta. In other words, the radius, which is fixed, all points along the ring are the same distance from the origin. But we are going to be summing, just like in the previous problem, dx, where we told it where the first x begins, where the last x ends, for where the charges are. Same here, 0 to 2 pi. So here, this would be equal to a d theta instead of 2 pi d theta. Well, that means that we can now write lambda, dq as equal to, let's see, dq is equal to big Q over 2 pi a times a d theta. And these a's cancel out. So here, dq can be written as simply big Q, oops, we've switched to another color for some reason, over 2 pi. Of course, the a d theta here got canceled out because there was an a here that would cancel, see, this a canceled that a, and this is the same d theta here as we've seen here. And so the whole thing just works out to be d theta right here. So dq is given by this value right here. Okay, now we want to put our proton at the origin, and we want to ask ourselves, in what direction would that proton experience an electric force due to this little quantity of charge dq, which we know is positive? Well, it would feel a force away from dq, but we're going to call this dE. Now, here's the important thing. Notice that dE has components. If we allow theta or phi, whichever we wish, well, we started with theta, so we'll write theta. And by the way, this is d theta right here. If this is theta here, we can see that we've got a dex, and a dey. Now, here's where I'm going to stop, and I'm going to show you the symmetry of this situation. Suppose that instead we had chosen this to be our our dq. Well, then this would be our d theta right here, and we would have a dE that would point along this direction, having components dey and dex. Notice that this dex would cancel this dex. But then when we come over here, we would have the cancellation of the deys, and so effectively, every quadrant of this ring along the xy coordinate system cancels in x's and y, the components of the electric field. But we want to go ahead and just prove that, since this is as much an exercise in setting up a problem and working through the integration, setting it up and working through the integration. So let's go ahead and write dE magnitude as k dq, And this time, all the dq's are a fixed distance a squared from the origin. See, before we had x squared where we said where does x begin, where does x end. Here, they are all at a distance a. And now we write k, dq, this is dq right here, is big Q over 2 pi d theta. And then we have an a squared to take into account. Okay, so k times dq being big Q over 2 pi, times d theta, sorry, we're not going to include d theta here because this is dq right here, divided by a squared. Well, let's go ahead for the time being and just write dE in terms of the components. Let's say that we don't necessarily know that these components will cancel each other out in every single quadrant. Let's just say we have a dEx, which is dE cosine theta. We have a dEy, which is a dE sine theta. Let's put our I hat and our j hat. And let's just see how we would set up these integrals. Well, E then would be the integral of dE. Ex would be the integral of dE cosine theta I hat. And Ey would be the integral of dE sine theta j hat. Well, dE itself is k big Q over 2 pi a squared. These are all constants, can come out of the integral. So then this right here, let me just put a multiplication, becomes d theta cosine theta I hat, that's for the first, plus d theta, integral, sine theta j hat. Our theta is going to go from 0 to 2 pi, 0 to 2 pi. Now, when we go ahead and carry out the integration, d theta cosine theta is sine theta. And when we enter these endpoints, sine of 2 pi is 0, sine of 0 is 0, no contribution from Ex. Next, we conduct the other integration. We get minus cosine theta. When we put in the endpoints, minus cosine of 2 pi is minus 1, minus cosine of 0 becomes plus cosine of 0. Well, minus 1 plus 1 is also equal to 0. So in fact, the electric field at the origin of this symmetrical distribution of charge is 0. Now, what if we were to erase one part of this ring? In other words, if we only had a semicircle worth of charge, how would the result differ? And of course, this time we would have to consider that while we would have contributions of dq here, which would give us a dE here, we would have contributions of dE here, which would give us contributions of, we'd have dq here. This would be our dE. This would be our dE. Notice that when we break these up into components, this is our dEy in the negative y direction, dEx, dEx, and notice what happens to the dEx. They cancel, but the dEy's add. So in other words, this would no longer be true that both the x and the y components of E would be 0. So finally, we get to the last problem in this chapter set of problems. And this problem gives us the same ring with the same uniform positive charge, but it says now we want to determine the electric field at a point P, which is a distance x. This distance is not variable. X is not variable. It's a constant. It's fixed. From the origin of the So it's along the axis of the ring, but a distance x from the origin of the ring, from the center of the ring. Well, here, to save ourselves a lot of labor, we can go ahead and play the same game of symmetry. And what we notice here is that when we use this dq here, we get a dE with an x component. See, this is along the x-axis. And let's call it a y component, which is downward. What happens when we get a dEq here? dq here. Well, let's just see. Then we are going to get a dE in this direction, which is going to have the same dEx along the same direction, but the dEy will be opposite. And so the dE perpendicular, as our book calls it, these will cancel out. And we only have to worry about calculating dEx. So let's see. Well, we know dq, and this time we're going to let this distance here, let's call this angle phi, or d phi, because our book's using this angle as theta, which is not the same as this angle here. So we'll call this d phi. Well, dq will be equal to lambda times ds, but ds is going to be a d phi. Okay? And of course, we know that lambda is equal to capital Q over 2 pi a. Okay, total charge over total length. And so we can make that substitution here for lambda, and you can see that the a's are going to cancel, and this becomes Q over 2 pi d phi. And that's our dq. Well, to save ourselves all the work, we can go ahead and make note of the fact that dE, magnitude-wise, is equal to k dq divided by the distance of separation squared. Now, look at the distance here. We've got our point P is here. We've got x, which is fixed here. We've got a, which is fixed here. Well, the distance of separation between this dq and p is r. And r is nothing more than, r, and it's the distance of separation squared, so it's r squared. So r is the square root of a squared plus x squared by Pythagorean. And if we square that, we get a squared plus x squared. Make our substitution for dq, and that gives us k times, let's see, what did we have? Let me just come up here real quick. It's going to be Q over 2 pi, and we've got a d phi here, and then we've got a squared plus x squared here. Okay, now, once again, we only have a dex component. We don't need to worry about dey because that's not going to exist. So we want de as a vector is only equal to, let's see, is it along the positive direction? Yes, it is. So positive k q d phi 2 pi a squared plus x squared, and x here is not a variable, along the and then we need the cosine. See, because this is our dE, but we need this to multiply cosine theta, because that's how we're going to get this right here. This whole thing is dex. Well, we can write cosine theta in terms of what is given to us here. Cosine theta is equal to x, the side adjacent to the angle, divided by the hypotenuse, r, which is the square root of a squared plus x squared. So come back down here and make the substitution for cosine theta plus kq d phi over 2 pi a squared plus x squared times x over the square root of x squared plus a squared. Well, we're ready now to perform our integration, integrating both of these. And by the way, let's just put a little I hat there. We get e equals. Well, let's pull everything that's constant out of the integral. K is constant, Q is constant, d phi is not constant, x is constant, 2 pi is constant, a squared plus x squared times square root of x squared plus a squared is constant. Remember, x is a constant here. Don't be fooled by the fact that they used x. In fact, it would have been better if they would have used like the letter D or the letter B, anything to prevent us from being confused about what x really represents and which is a constant. Now, I've taken a squared plus x squared and multiplied it by half, square root, which gives me 3/2. And of course, my charge, it's a full ring, 0 to 2 pi, which gives my integral a value of 2 pi. My 2 pi cancels that 2 pi, and the solution for the electric field equals kqx over a squared plus x squared to the 3/2. A little bit tougher of a problem, but we use symmetry to simplify the process for us. Well, this concludes the second part of the problem solving for chapter 23. Until next time.